Today we are going to be learning about reflection and refraction and how they differ from one another. Let's start by defining each of the terms. Reflection is the throwing back by a body or surface of light, heat, or sound without absorbing it. In simpler terms, this means that when a light ray is directed towards an object or surface, the entirety of that same ray will reflect away from the surface or object, and none of it will be absorbed. A common example of a reflection is the reflection you see when you look in a mirror. Refraction is the fact or phenomenon of light, radio wave, etc. being deflected and passing obliquely through the interface between one medium and another, or through a medium of varying density. In simpler terms, this means that when a light ray is directed towards an object or surface, that ray will pass through the object. While it does so, it will bend. A common example of refraction is the displacement of an image you see when you place a pencil in water. Now, let's discuss reflection and refraction more in depth. For this video specifically, we will focus on reflection and refraction of light rays. As stated previously, reflection is light rays bouncing off a medium and not being absorbed at all by that same medium. Let's start by defining some of the characteristics of a reflection. This picture illustrates a beam of light being reflected off of a mirror. The beam of light coming from the laser here is called the incident ray. And the beam of light being reflected from the mirror is called the reflected ray. And the line here is the normal of the mirror, which is simply a line, ray, or vector perpendicular to an object's surface. The angle here is called the angle of incidence and is represented or expressed by theta I. The other angle here is called the angle of reflection and is expressed as theta R. It is important to point out that both angles are drawn in relation to the normal of the mirror. The law of reflection states that the angle of incidence, theta I, and the angle of reflection, theta R, are equal to one another. Something that is frequently overlooked by many is that there are two different types of reflection. These two different types are called specular and diffuse. This picture is an example of a specular reflection because the surface is smooth. With a smooth surface, a well-defined beam of incident rays will result in a well-defined beam of reflected rays going off in one specific direction. An example of specular refraction is when light is reflected off of a mirror. This picture is an example of a diffuse reflection because the surface is rough. With a rough surface, well-defined beams of incident rays get reflected in many different directions. This allows the spectator to see reflected rays from many different angles. Diffuse reflection occurs when light is reflected off of a surface that doesn't produce an image. The majority of things we visualize are due to a diffuse reflection. This type of reflection allows us to perceive direction and distance. Even though specular reflection involves a smooth surface and diffuse reflection involves a rough surface, the law of reflection applies to both specular and diffuse reflection. Let's try an example problem to make sure we understand how to calculate incident and reflected rays properly. Feel free to pause the video and try to solve this on your own. Okay, hopefully you were able to solve this on your own. If not, let's figure it out together. So, this line right here is the normal to our surface, so we know it's perpendicular. Anything that's perpendicular is a total of 90 degrees. If we already know that this angle right here is 10 degrees, we know that 90 degrees minus 10 degrees is 80 degrees. So our angle of incidence here is 80 degrees. Because of the law of reflection, we know that the angle of reflection is going to be the same as our angle of incidence. So we know that our angle of reflection is going to equal 80 degrees. What type of reflection is this? Well, because we have a smooth surface, this is a specular reflection. Okay, now that we have a basic understanding of reflection, let's learn more about refraction. As stated at the beginning of this video, refraction is light rays being deflected or bent when they pass through mediums of varying densities or indexes of refraction. Let's start by defining some of the characteristics of refraction. This picture illustrates a beam of light that is bending as it travels from the air into water. The beam of light coming from this laser here is again called the incident ray. And the beam of light being refracted in the water is called the refracted ray. Now, let's point out the normal to the water, which again is just a line, ray, or vector perpendicular to the object's surface. The angle here is called the angle of incidence and is expressed as theta 1. The other angle here is the angle of refraction and is expressed as theta 2. Notice that both of them are drawn in respect to the normal of the water. I would like to point out the equation that I have at the bottom of this page. It is the equation for the index of refraction. The index of refraction, simply put, is how easily light rays travel through a material. The greater the index of refraction, the more the light ray will bend when it travels through the material. Here is a table showing you the index of refraction for some common items. The index of refraction for air is very close to 1. Based on this table, we can infer that if we have two light rays traveling through air and one of them hits water and the other hits a diamond, the light ray that hits the diamond will bend more because the diamond's index of refraction is greater than that of water. At this point, you might be asking yourself, how do I know which way a ray of light is going to refract? Well, here is a simple method you can use to help yourself remember. Imagine you are driving a vehicle on the pavement, and all of a sudden you hit a muddy surface at an angle. The tire that is stuck in the mud, which is this one, will go slower and will cause the car to pivot until eventually both tires are fully in the mud. This is what happens when a light ray enters a material with a bigger index of refraction. Something very similar happens when light rays escape a material with a higher index of refraction and enter a material with a smaller index of refraction. However, in this scenario, the car you are driving is already in the mud, and the tire that hits the pavement first causes the car to rotate and pivot in the opposite direction. Just like reflection has the law of reflection, refraction also has a law, but it is more commonly known as Snell's law. Snell's law allows us to define a relationship between the angles of incidence and the angles of refraction, as well as the differing materials' refractive indexes. This relationship is shown in the formula pictured. The signs of the angles and the indices of refraction have an inverse relationship. This means that if the index of refraction, expressed as N1, increased, then the sign of the angle of incidence would decrease. Let's try an example problem to make sure we understand how to use the refractive index of materials to find the angle of refraction or angle of incidence. Feel free to pause the video and try to solve this on your own. Okay, hopefully you were able to solve this on your own. If not, let's figure it out together. The question states that light passes from air into glass. So the first thing that I did was show that light is passing from air into glass. We know, based on the refractive indexes, that it's almost like the car is going from pavement to mud. So we can draw the line of the ray as such. It also gives us the refractive indexes, which I've put next to each material. It mentions that the angle that the light enters the glass is 35 degrees from the normal of the glass, which right here would be our angle of incidence. So we are solving for our angle of refraction. We're going to be using Snell's law to solve this. I've put the accompanying values to each of the numbers in our equation and set it up as follows. The first thing that we do is times these two values together, which gives us this number. The next thing that we do is divide by 1.52 on both sides. This gives us the value for the sine of theta 2. In order to get theta 2 by itself, we must take the inverse sine of this value. This gives us theta 2, which is our angle of refraction, which is 22.18 degrees. This concludes our video today on reflection and refraction. Thanks so much for watching.